Welcome, and in this video we're going to be introducing you to the wonderful world of partial derivatives. Here we have a picture of gumbo. Unfortunately it's not Dr. Link's gumbo, but it still looks pretty good nonetheless. Anyway, on to the good stuff. Now recall from your pre-multivariable calc days, also known as the dark days, you could take the derivative of any function really with respect to x. It was kind of a hassle though to do it with other functions because you'd end up having to do implicit differentiation. But with partial derivatives, this is no longer a problem. Now with partial derivatives, the symbol is kind of like a curly D. So to our left here, we have the partial derivative of a function with respect to the variable z. Of course, this could be any variable. We just kind of arbitrarily chose z there. There's another form of notation which is located on the right. As you can see, we have the function f of xy. If you wanted to take the partial derivative with respect to x of the function f, you would write f sub x. Likewise, if you wanted to take the partial derivative of the function with respect to y, then you would write f sub y. Now, how do we take partial derivatives? Well, we take any other variables that we're not taking the derivative with respect to as a constant. So say we have 9x squared z cubed, and we want to take the x partial derivative of this function. Well, what do? We set z cubed as a constant. We take that as a constant. And 9 is clearly a constant because it's a number. And then we take the derivative of x squared, which we know is 2x. So we have 9z squared times 2x, which is equal to 18z cubed. I said squared before, I meant cubed. Z cubed x, and that's our answer. Alright, now I'd like you guys to try it on your own on this next slide, so I'll give you a couple seconds. And we're back. Alright, for the first one, when we take it with respect to x, we have y cubed as our constant, so we multiply 7y cubed times the derivative of x squared, which is 2x, so we have 14y cubed x. And when we take the derivative of the function with respect to y, we have x squared as our constant now, and we multiply that times the derivative of y cubed, which is 3y squared. So we have 21x squared y squared. Again, just like derivatives from the Dark Ages, you can also take second-order derivatives, third, fourth, and so on. But note, with partial derivatives, you can have mixed partials, which basically means that you could take the partial derivative with respect to x of a function, and then with that partial derivative, you can take the partial derivative of that partial with respect to y. So what does this kind of look like in terms of notation? It looks like this. Now the order of the variables in this notation means that you'd first take the partial derivative with respect to y, and then the second one, and then you would take the partial derivative with respect to x of that first partial. Note that if the problem is written like this in the other type of notation, note that the y actually is on the left this time instead of the right. And in this notation, you would go from left to right in terms of partial derivatives. So you would take the y partial derivative first, and then you would take the x partial derivative second. So what's this look like? I'll give you guys a couple seconds to try this out on your own. And we're back. Alright, so let's take the x partial derivative first. And we know that that's 12x squared y squared plus 12y x cubed. Alright, and then to get the second partial derivative with respect to y, we just take the y partial derivative of f sub x, which we know is 24x squared y plus 12x cubed. And now to get the other answer, we have f sub y, which is equal to 8x cubed y plus 3x to the fourth. And when we take the x partial derivative of that, we find that it's 24x squared y plus 12x cubed. But wait, look at the same answers. Look at these answers. They are the exact same. Now, why is that? Well, that is because it's a theorem called Clairaut's theorem, which states that if second mixed partial derivatives are continuous at a point a comma b, then the partial derivative f sub xy of a comma b is equal to the partial derivative of f sub yx of a comma b. Anyway, this is where we're going to end the video. I hope you enjoyed watching. Thanks a lot for watching.